Well, hello, eager students. Today
Hello.
we're going to work on section 4.6, and notice the title, The Fundamental Theorem of Algebra. That means it must be pretty important since it is fundamental, and Descartes' Rule of Signs. Well, let's look at a little introduction idea. Introductory thought. What if you were asked to find all of the solutions of our function here, x to the fourth minus 15x squared plus 10x plus 24? We have some tools from last semester we remember. First of all, we can see that the degree is 4, and our leading coefficient a is positive, and so all that together means that our shape is going to be something like this, opening up and maybe looking something like a W or some kind of form of that. All right, that's one thing we know. Second thing is we can, it's up or for my students we did high, very good. Second thing is we recognize we can use synthetic division. We can always try that. So that means finding our possible rational roots. And if we look at that, remember it's all factors of the last over all factors of the first. So we're talking about what? Plus and minus. 1, 2, 1, 2, 3, 4, 6, 4 and 6, 3, 8, 12, and 24, commas between all those. All of that over our factor of our first one, which is simply 1. Okay? So that's all of our numbers, plus or minus 1, 2, 3, 4, 6, 8, and 12. And we're going to condense time by not writing the plus or minus before all of them because that's just silly. It's time consuming. We know what we mean. So that's everything we're going to try. And let's remember our third tool that we would do is we would get this down to quadratic form, and then the cool thing is once we're in quadratic form, we can either factor or use quadratic formula. Now, I did QF. Here's the problem. If we look at how many we have to try, do you see, if we look over there, how many possibilities is that? 16. Do you realize? And that's just the pretty roots. But that's just 16 things we might have to try before we can see if we have a solution or not.
Our motivation for our lesson today is,
ding, 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 you got that, is that we are going to reduce the number of things we have to do in order to find our solutions, because we would not want to have to try all 16 things, roots. Okay. So let's remember, complex numbers were created to solve our equation I squared equals -1. The fundamental theorem of algebra says every non-constant polynomial, a non-constant polynomial is one that has x's in it. Every non-constant polynomial has a 0 in the complex number system. Okay. Second major concept, factorization. This says if we have a polynomial with degree n bigger than 0, so again, not a constant polynomial, x to the first power, x to the second, and so forth, then there are n, not necessarily distinct, which means different in mathematics, complex numbers or solutions such that we can factor the thing. So with complex numbers, we can actually do some factoring. And then the last major concept is that every polynomial of degree n greater than 0, again, non-constant polynomial, has at most n different zeros. In the complex system, if you recall last semester, we talked about the fact that if you had x to the 5th, there were at most 5 solutions or 5 roots. So this is building on that idea. All right, that's a lot of crazy words there that look hard, and we're going to show you how to make it easy.
example 1. Find a polynomial f of x of degree 4 such that -3, -1, and 2 are zeros. 2 is a multiplicity of 2, and f of 1 equals 32. Now this is something we did last semester, so we're just going to refresh your brain on this. Okay, so we've got a degree 4, -3, -1, and 2 are zeros. So that means that x plus 3, x plus 1, and x minus 2 are factors. And it tells me that 2 is a multiplicity of 2, so that means that x minus 2 is squared.
And there's just one other part of the problem that is a problem for us, and that is f of 1 is 32.
The leading coefficient.
We use the f of 1 equals 32 to find our leading coefficient.
Now, we know that from last semester, f1 equals 32 means plug 1 in for x, and then that would be 32. So 32 equals a times 1 plus 3 times 1 plus 1 times 1 minus 2 squared. Now,
we're just going to go ahead and get to the work there without explaining all of this algebra because you know how to do it.
so this becomes, later on, this becomes a times 4 times 2 times negative 1 squared, which becomes a times 8 times 1, which is 8a. So 32 equals 8a, so a equals 4. So our leading coefficient is 4, so f of x equals 4 times x plus 3 times x plus 1 times x minus 2 squared. And that is our polynomial that we were looking for. Now what does this look like? This also, if we go ahead and plug in 0 for x, we would get our y-intercept. So f of 0 is 4 times 0 plus 3.
Just write it.
0 plus 1 is 1. 0 minus 2 is negative 2 squared. And that would give us 4 times 3 is 12. And then negative 2 squared is 4, which would be 48. So 0, 48 is our y-intercept. So that's going to be way up here. So right there is 48, and that's our y-intercept. Now we know that we have zeros at negative 3, negative 1, and positive 2. We'll put that right about there.
What's happening at 2?
It's a double root. It's a multiplicity of 2, so it's going to bounce off of the x-axis.
It's going to have parabola type behavior there.
All right, so here, here, and here. Okay, this is going to look linear, this is going to look linear, and this is going to look like quadratic. And we know that since a is positive and it's an even degree, that it's going to have a high-high relationship, or a high-high end behavior. So it's going to come through this, go up through here, come through that, and then bounce off of here and go up.
And we don't really know if it's at a relative max there at 48, but
we're going to...
You need calculus for that, or a calculator.
So it's going to look something like this. We're not quite so sure, but yeah.
Okay, so that's old, but we need to remember all that. And now you're going to go to section 4.6 in your textbook and work problem number 27.
All right, next.
So yes, last notes, we remembered that i's come in pairs because they come from the discriminant, the plus or minus square root, and if you have a negative under the square root, that's what gives you your two i's. So if you have one complex solution, you have to have two. And last section, we talked about that is called the conjugate. So now if you pursue mathematics, if you continue in math somewhere down your career, you're going to see that we actually call that z. A plus bi is usually called z, and then its conjugate, we call it z bar, with z with a bar over it. So just giving you some extra notation. So we're going to find the zeros of this one. And again, this is something you know how to do from algebra. Recognize that we have actually got here a quadratic and the leading coefficient's positive. So we know this is a quadratic parabola opening up, and we can just use quadratic formula because we can see this does not factor. So negative of negative 4 plus minus square root of the quantity negative 4 squared minus 4 times 1 times 5 all over 2 times 1. Now we're going to save time and not work all this out because honestly you should be able to do that by now. You can get the next step, we're going to get 4 plus minus square root of negative 4 all over 2. And that, as you can see, lets us see that we don't have any real x-intercepts. So this is not going to cross the x-axis because of that. And after last lesson, you know that this is going to finally reduce down to 2 plus or minus I. And there is our solution of 2 roots. Now, so we know it's not going to cross the x-axis. What else could we figure out? Down here, we also can find the vertex. Remember that the vertex is x equals negative b over 2a. That gives us the x-coordinate. And we get negative of negative 4 over 2 times 1. And with all your simplifying, that becomes 2. And when we plug that in, our vertex actually becomes the point f of 2. Oops. There you go. F of 2 is 1, so we get the point 2, 1. So there's our vertex, and if we go up and plot our vertex 2, 1, and we can see that we have no roots because this is opening up like a cup, one other point that can really help us graph this is the y-intercept. And if we look over here, we can find that our y-intercept, when we plug in x, everything drops out but the constant, so our y-intercept is the 0.05. So what we have here is our parabola that is going to look something like this. Okay? So this confirms what's going on when you have imaginary solutions. They are solutions in the complex number systems, but the function does not cross the x-axis. Now we have to bring all of this knowledge to what we're doing now, our new material. Except first you're going to work two problems from the textbook. Notice that number 17, it says to factor that one first, okay?
Welcome back. Now we're going to find a polynomial with real coefficients whose zeros include the numbers -3 and 2 minus I.
Oh wait, I see an I. What do I know?
I's come in pairs.
So if 2 minus I is a root,
then the conjugate is also a root. So if z is 2 minus I, that looks weird, then z bar equals 2 plus I.
Hey, wait, we saw those before. In fact, this is one reason we did the last example. These two solutions we got from that polynomial x squared minus 4x plus 5. Now, we're going to save a little bit of time in this problem by using that, and then we're going to show you the aloha work in a little bit with how that works. But we now know what?
That this is a factor of the polynomial. So since x squared minus 4x plus 5 is a factor and the other 0 is at x equals -3, then my other factor would be x plus 3 and x squared minus 4x plus 5. So I've got the zeros at 2 minus I, 2 plus I, and at -3.
Right, so we can actually plot the -3 on our graph. And the other thing we can know is that if we look up here in our polynomial, when x is 0, we're going to get f of 0 equals 3 times, and all the x terms drop out, 5, so we're going to get 15. So we know that this function is going to cross through at 15. And another thing, if you look at the function, notice the leading coefficient is +1. So we can see this is degree 3. And a is positive, so we're going to do a low to high thing. And the only time that we can cross the x-axis is at -3. So we need a little bit more information in sketching this. Well, actually we don't really. It's going to look like this. And again, see that we've got it's that kind of curve. Now, actually, again, in calculus, you would learn a little bit more about why the shape curve is like that. Now, one question you might be asking is, how do I know if 2 minus I is a 0 and 2 plus I is a 0? How do I actually write this as factors? And this is a skill you do need to know, so now we're going to show you the aloha work. X minus 2 minus I would have to be in parentheses, and then x minus
Oops. Oh, that's right.
because we're going to simplify, minus parentheses 2 plus I. Okay, that's what it means if we say that 2 minus I is a solution. It solves the factor x minus the root. And if 2 plus I is a solution, it solves the factor x minus the root.
I mean, we've been doing that all semester with this whole x plus 3 is a factor, x minus 3, x equals -3 is the root.
Yeah. Now, what would be logical if you had to do it here? We didn't ask if you wanted to, but if you had to, wouldn't it be to just distribute those negatives? And now we get what the next step is that Ms. Miller was writing, x minus 2. That becomes a plus I when we distribute, and parentheses, x minus 2 minus I. And we leave it to you to do the grunt work on that. But if you noticed, do you notice that if we were to regroup, look at that right there, x minus 2 and x minus 2, and you have x minus 2 plus I and x minus 2 minus I, isn't that look like a difference of 2 squares? So you could actually do some very creative multiplying here. You could either term by term distribute or use a pattern.
Okay.
And now you get to do a couple of problems.
All right. Come back when you're done. All right. Example 4.
We're going to completely factor this function over the set of real numbers, given that we know 2 minus I is a 0. Really cool. We actually have already used part of this before. We know that 2 minus I is a 0, so we also know that 2 plus I is a 0. We are trying to make it easy by repeating some things. So we know from the two previous examples that those two solutions give us the factor x squared minus 4x plus 5. Now, what would our next step be in working a problem like this, Ms. Miller? What would the next thing we want to think about be?
Well, since we have this really long problem, we need to figure out what the possible rational roots would be. So, we've got the possible rational roots would be the factors of 35 plus or minus over the factors of 1.
And we don't need to write the over 1 because when it's over
we know
1,
that.
we're done with that.
We've got 1, 5, 7, and 35. So we have a total possible rational roots of 8.
So now we're going to use our beautiful synthetic division shorthand, and we're going to try some numbers. So let's remember with the coefficients, we've got to notice that we don't have any terms missing, so that works out nicely. So we're lazy. We like to start with positive, beautiful numbers. So we're going to try 1. When we plug in 1, bring down the 1. And again, 1 times 1 is 1, plus negative 4 is negative 3. 1 times negative 3, plus negative 2 is negative 5. 1 times negative 5 is negative 5, plus 28 is 23. 1 times 23 is 23, plus negative 35 is negative 12. Okay, not a solution. Blah. Let's try 5. Again, we like to start positive small numbers. So let's try 5. And we're going to save the work of telling you how to do it and just write out the row that we get. We get 1, 1, 3, 43,
180.
1, 3, 43, 180. Oh, yeah, I was reading.
We're good.
Hey, wait, what do we notice here?
Well, they're all positive.
And what number did we substitute in?
5, a positive number.
So when we substitute in a positive number and the row is positive, do you remember from last semester what that's called?
X equals 5 is an upper bound.
Oh, what does that mean?
That means that no other roots are bigger than that.
So we're not even going to waste any time trying positive 7 or positive 35. So now we're done with trying our positive roots that are pretty. So we're going to try negative roots. Let's try negative 1. Again, saving the time of the explanation, our row is 1, negative 5, 3, 25, and negative 60. All right, not a solution, but just for further reference, remember that does give us the point, negative 1, negative 60. That is what that means.
Yeah, and this one up here would be 1, negative 12.
Yeah. Okay.
It's on the graph.
Yeah, it's on the graph. Okay, and so once again, we're going to try negative 5 and saving the time with the multiplication. We get 1, negative 9, 43, negative 187, 900. But wait a minute, we substituted negative. And what happened?
They're alternating signs.
So
x equals negative 5 is a lower bound. Now remember, every time we're doing the synthetic division, we're using the original problem since we didn't find any factors.
Right, that's a good point. So now we know we're not going to try negative 7 and we're not going to try negative 35. And here is our problem. Every possible beautiful root that could have worked
is in between. We just eliminated them.
Yeah, so none of them work. So what do? Well, we do have one other tool here. We do have a factor. X squared minus 4x plus 5 is a factor, so now we're going to do long division. And once again, sparing you all of the work, we're just going to write out the steps and save time with not explaining every single step because you should know how to do this. We're going to multiply by x squared.
So
and
you
it
get
gives
x
us
to
fourth minus 4x cubed plus 5x squared. Draw a line, change all the signs, and add.
So now
we get negative 7x squared. Bring down the next term, plus 28x minus 35. Again, we're going to plug in negative 7 up there, and it gives us negative 7x squared.
No, 7x squared. Oh,
negative 7x squared plus 28x minus 35. We can see if we changed all the signs, we'd get 0. So what do we have? That's the other factor. Ooh, well, I know this isn't pretty, but isn't that a DTS, a difference of two squares? Yep, and it does factor x plus square root of 7, x minus square root of 7. And what do we know? We have that a square root of 7 is about 2.6. And what did we find? Go back up here. We found that x equals 5 is an upper bound, so there's no solution past that, bigger than that, and x equals negative 5 is a lower bound. And do you see that plus and minus 2.6 fall in that realm? And our graph is going to look something like this.
Here's negative square root of 7. positive square root of 7?
Again, we've got kind of a W-ish kind of a shape. Sometimes it's a little skewed, but A is positive and it's degree 4, so this is high, high. So it's going to do something like this.
Oops.
There you go.
Kind of like that.
Something like
A
that.
little weird, but
yeah.
Anyway, if you want to see what this is doing, go to your calculator and type this in and
Graph the whole
graph
function.
the
You get a
thing.
better graph.
Yeah.
Okay. So guess what? We have another rule which actually helps us narrow down. I mean, the whole point that we started out with is you don't want to have to try every single one. It'd be nice to know if we've kind of reached a point where we don't try something else. So Descartes' rule of signs is really a neat thing. It says the number of positive real zeros is either equal to the number of sign changes in your polynomial or less than that by a multiple of 2. Now, I know that sounds crazy, but we'll show you that in a minute. And the number of negative real zeros is equal to the number of sign changes in P of negative x. So we actually have to substitute negative x in first and do a little algebra. Or less than that by a multiple of 2. So I'm going to show you how to do that right now. Let's write out P of x, our polynomial, which is f of x. Unfortunately, I called it f of x. P of x is 2x cubed minus 17x squared plus 22x
is this the previous?
minus 7. Oh, wait,
Oh,
sorry. I'm looking at a different...
No, this one? Okay.
Previous example, yes.
This is the same one that we did earlier.
Yeah, so now we're going to, f of x, rewrite it. F of x, equals x fourth
Oops.
minus 4x third minus 2x squared plus 28x minus 35. Okay, now let's look at the sign changes. From the first term to the second, it goes from a positive to a negative, so there's one sign change. From the second to the third, it doesn't change. From the third to the fourth, it changes. And from the fourth to the fifth, it changes. So what do we see here?
So there's
three sign changes, and it goes 3 sign changes, and if you go back up here in the original polynomial, it says it's either equal to the number of sign changes or less by a multiple of 2. So 3 or 1 positive roots, and we're going to fill that in our chart. Now, why would that be? Because i's come in
pairs.
All right, now let's look at f of negative x. We have to actually do one step of work here, and that is in our polynomial, substitute negative x in.
Minus 35.
And we have to do the work. So that's going to give us x to the fourth. Okay, that is a negative x cubed when we raise it to the power times a negative 4 gives us 4x cubed. A negative x squared becomes positive times the negative 2 is still negative. And a minus 28x minus 35. Now let's count sign changes. From first term to second term, did it change?
No.
No. Second to third, yes.
That's it.
So what do we know?
There's
One
only
sign
one.
change. So there's no one sign change.
One sign change is one negative
Root.
root.
Now, let's look at filling in 1 right here. Do you see that if we have 3 positives and 1 negative, there can be no imaginaries? So we're going to put 0 in. Why is that? Because we have a degree of 4, and each row has to add up to the degree. So if we go down to the next row, we have 1, or another possible ability for our roots is 1 positive, 1 negative, and 2 imaginaries. Now, what did we find in the last example? In the last example, we found our roots to be x equals plus or minus square root of 7. So one of those was positive, one was negative, and then we started out with 2 imaginary roots.
So that one looked like that.
This helps us tremendously because we knew how to negative root, and now we can work a couple of problems with that. So it says use Descartes' rule of signs to determine the possible number of positive and negative roots, and then find all the zeros. Okay, so our first polynomial, we like to rewrite it so we don't get confused. You know, we can write all over the work.
Okay.
Okay, let's check sign changes. Did it change? Yep, once, twice, 3. So there's 3 or 1 positive roots. All right? Now let's do P of negative x. Okay, plugging in negative x. Don't skip the step where you actually plug it in because it'll save you careless error mistakes. Yeah. Okay, so this becomes negative 2x cubed. That's still going to be a negative 17x squared minus 22x minus 7. Ooh.
No sign changes.
Oh.
So there's no negative roots.
Now, what matters about that that's really cool is...
That's really neat, because if I try to do the possible real roots, now I can just eliminate all of the negative ones. Because they're not going to be part of my solutions.
And let's finish out our chart. Since it's a cubic polynomial, if there's 3 positive roots, there cannot be any imaginaries. And imaginaries or i's come in twos. They come in pairs. So that's why, hopefully, you can now see if we have 3 or 1 positive root, the reason we go down by a multiple of 2 is because the imaginaries go up. All right, so now we're going to try our possible rational roots. Our possible rational roots are all factors of 7. So plus or minus 1 and 7 over all factors of 2, plus or minus 1 and 2. Well, the thing is, we already know not to try any negatives, so what is all of our possible roots? We're going to try 1 and 7, and then 1/2 and 7/2. And now we're going to go to our synthetic division, and there's no missing terms, so this is a pretty easy one. So 2, negative 17, 22, and negative 7. Again, I'm kind of lazy. I like to start with 1. And our row becomes 2, negative 15, and 7 when we do that, and 0. And so, cool, x equals 1 is a solution. Now, look, it was a cubic polynomial. So we now have, what we have left is factorable. And it turns out that it factors to 2, it's 2x squared minus 15x plus 7, and you can spend time, it factors to 2x minus 1 times x minus 7. And now we have all of the factors and we have all of the solutions. So one solution is at 1, the other is at 1/2, and one at 7. And what do we know about this? A is positive, and degree is 3. So this is a low to high shape.
And my y-intercept
yeah,
is 0, negative 7.
And so our shape looks something like this. Beautifully drawn. And just make that y-intercept bigger, so yeah, it's hard to get it right there. There you go. Yeah, there we go. When in doubt, make it really big. Okay. All right. Use Descartes' rule of sign. Okay, so this one, we're just going to use it, get practice using it to determine possible number of positives and negatives. Okay, we're not going to do an entire problem here. All right, here we go. So let's do p of x.
Okay.
It's 2x to the 4th. Plus 15x cubed plus 31x squared plus 20x plus 4. Hey, what do you see?
No changes in sign.
So it would be helpful to just write 0 positive roots and maybe put a box around that. So that reminds you. So we're not going to try any positives if we were going to solve this whole thing. And now let's do p of negative x.
Well, we don't know how many.
We don't know how many, so we want to.
I mean, I know that there's 0 positive roots, but at this point, I don't know how many choices I'm going to have, so I need to figure out the negatives.
Yeah, it's actually better to do both of them before you start filling that chart out. P of negative x is 2 times negative x to the 4th plus 15 times negative x, negative,
Can't find my
cubed, yeah, plus 31 negative x squared plus 20 times negative x plus 4. And this becomes 2x 4th minus 15x cubed plus 31x squared minus 20x plus 4. And let's look at sign changes now. There's 1,
2,
yep,
3, 4.
That means there's 4, 2, or 0 negative roots. And now you know how to fill this out. We know in our negative column we have to put 4, 2, or 0. And in our positive column we have 0 for each case. And what's happening with I? Our degree is 4. So our row has to add up to 4. So there's no imaginary roots if there's 4 negatives. There's 2 imaginary if there's 2 negatives, and 4 imaginaries if there's no negatives at all.
All right.
And now, one problem with all the whistles and bells. Here we go.
It says find all the rational zeros, find the irrational zeros, the complex zeros, if any. Whenever appropriate, use the rational zeros theorem, the upper and lower bounds, Descartes'
Descartes goes before DeHorst. Descartes'
Okay.
rule of signs.
the quadratic formula or other factoring techniques. Okay, so here we go.
First thing is, A is positive, degree is 4, it's going to be high, high. All right. Next, let's list our possible rational roots.
All right, so that would be the factors of 20. So that would be plus or minus 1, 2, 4, 5, 10, and 20 over the factors of 1, which doesn't matter. So we've got all of those lovely numbers.
And next, we're going to use Descartes' rule of signs. So looking at P of x equals x fourth plus minus 5x cubed plus 2x squared plus 22x minus 20. And let's look for sign changes. I see
1, 2, 3.
Okay, so we're going to write underneath there 3 or 1 positive roots. And we're not going to fill it in yet because we're going to have to see what happens. And let's put a box around or something. Yeah. All right, let's do P of negative x. And we're going to save the time. P of negative x becomes x to the fourth plus 5x cubed plus 2x squared minus 22x minus 20. If you want to take the time to do the work and make sure you can do it, that's fine.
So there's one negative root.
So we know there's going to be a negative root. Now, it may not be one of our pretty ones. It could be something like square root of 7, you know, something ugly, but there's a negative root. Now, how do we fill our chart out? We can see 3 is our highest positive root number, so we're going to
positive. I'm sorry.
So we're going to put 3 in our positive. And we
1.
know there's 1 negative, so 3 positives, 1 negatives means 0 imaginaries, or 1 positive, 1 negative, which would mean we have to have 2 imaginaries. All right, through our process of synthetic division, okay, we're not missing any terms, so it's on the top, 1, negative 5, 22, 22, and negative 20. We're going to start with 1 because 1 works. It's pretty. 1, negative 4, negative 2, 20, and 0. So 1 is a solution. We can try 1 again, but to save time, we're just going to go on down to another one that works. Negative 2 works. And we're going to use negative 2 with the with the polynomial right above. So maybe draw a new line. Okay, yeah. We're going to use negative 2 with that one because we already found a solution. And we get 1, negative 6, 10, and 0. So x equals negative 2 is a solution. And what we have left is quadratic. So that gives us x squared minus 6x plus 10. Well, for that to equal 0, we're going to have to use quadratic formula. And using quadratic formula, our solutions are going to be x.
Well, okay, one thing, if you look at the discriminant right here, you would see that b squared is 36 minus 4 times 10, 4 times 1 times 10, which is 36 minus 40. So this is going to be an imaginary number because that's negative.
Yes, and so ultimately we're going to get x equal to 6 plus or minus the square root of negative 4 over 2, and that is going to simplify to 3 plus or minus I. All right, okay. So now let's count our solutions. Yes, there we go. We've got x equals 1, x equals negative 2, and x equals 3 plus or minus I.
One thing that I want to point out here is that, okay, when we're looking at 1, we already found 1 was a solution. It was positive, so we could try 1 again, or try more positives, or we could try a negative 1 and then see, oh look, we've got a negative number that would be a solution. So, I mean, if you want to try a negative number to find the one that one is, I mean, it's up to you.
Yeah, and again, remember, they might not be one of our beautiful roots that is possible up there. It could be a really ugly number. Just remember that possible rational roots is only giving you the beautiful solutions. One other thing we can do is our y-intercept. You should be able to look at that and see it's the point 0, negative 20. Okay, and our graph is going to be funky looking. Again, you actually need calculus to get a really good feel with why it curves the way it does, but it's going to look something like this.
Not like that. It looks like that. And then it kind of Comes up, goes through that one, and then except it's not quite.
Does a little
all the way down.
curviness up there, and then there we go.
Does some funky stuff.
So it does kind of crazy stuff, but
And
that's it.
That's one right there.
Now, if you go to the next slide, when you do your ET problems, notice in this one, unfortunately, in section 4.6 in the book, it doesn't give you problems exactly like we're going to give it to you in the section, but it does in the chapter review. So we're asking you to do 2 that are in the section where they actually give you 1 0, so they save you a little bit of work. And then 2 in the chapter review on page 321 where you have to do all the whistles and bells.
Okay. All right. Your actions. By 8 a.m. the day you have class, you need to email your teacher the following information. 1 new thing you learned. There's a lot of new things I'm sure you learned.
Yeah.
So if you say, I didn't learn anything,
We're gonna call you a liar.
2 good questions. If you don't have questions on this, again, I think you should. And they need to be good questions. 3 old skills that are important to recall for this material.
And I can count about 10.
Yeah.
So.
And don't forget to bring your entrance ticket, problems, and completed notes when you come to class. See you guys later.